Hi there. So this is a video on Module 7 for Math 125. Module 7 covers 10.1 and 10.4, and it's on probability, specifically just the basics concepts of probability, and then some single stage experiments. So I'm going to start just by filling in these blanks. These are the book definitions. So let's kind of, we'll look at this and then I'll give you some more practical examples. So a probability experiment is a process that leads to well-defined results called outcomes. So what the heck does that mean? Well, I'll give you an example. Let's say we roll a die, a six-sided die. Let's say, we roll a die one time. Okay, there are 6 possible outcomes that could occur. So you could get a 1, you could get a 2, you could get a 3, you could get a 4, you could get a 5, you could get a 6. Those are the possibilities. So rolling a die one time would be considered a probability experiment, and you're going to get an outcome when you roll. That outcome might be you roll a 3, for example. And let's also define an outcome. So an outcome is the result of that single trial. So let's say again we roll that one die. Let's say we roll a die and we get a 3. Well, the 3, that's considered the outcome of the experiment. So the experiment is rolling the die and the outcome is the 3. Okay. For instance, let's do another example. When flipping a fair coin once. So when we say fair coin, and when you see that in your homework, that means you could get a heads or a tails. So think of just, a penny or a nickel or a dime. What are the possible outcomes if you flip a fair coin once? Well, you could get a tail or you could get a head. So these are the possible outcomes. There are 2 possible outcomes. And when we do this, we can ask ourselves probability questions from these outcomes. So for example, we could say, what's the probability of getting a tail? So this notation, P of T, just means what's the probability of getting a tail? The probability of getting a tail is 1 out of 2 because there are 2 possibilities and there's 1 tail. So 1 tail, 2 possibilities. So when we do probability experiments and we're asked to find probability, we always want to know what the total number of possibilities are, and sometimes it's easy to count, like in flipping a coin, it's very easy to see that there are 2 options, head and tail, but sometimes we have lots of different options. So that's where this fundamental counting principle comes in, and this helps us deal with situations where we have a sequence of events, and they can each occur in, more than one way. So for example, let's take this example down here with blood types. So we have 4 different types of blood type. You can be Rh positive or Rh negative. Okay. They also label it as male or female. So there's 3 different ways that we can label blood type. So I'm just going to draw 3 different dashes. Okay, and I'm going to label them. So this first one, we can label it with the type, we can label it with the Rh factor, and we can label it either as female or male. And so I could just ask you, well, why don't you make a list of all the different possibilities? So for example, maybe I'm type A, I'm Rh positive, and I'm a female. That's one possibility. Okay, maybe I'm type A, I'm negative, and I'm a female. That's another possibility. There are lots of different possibilities. Now, it's certainly possible to list all of them, but sometimes it's easier to use what's called the fundamental counting principle. And what this says is we can go through each one, and identify how many possibilities for each different description. So there are 4 different blood types, there are 2 different Rh factors, so positive or negative, and there are 2 different options, male or female. And then we can multiply those together. So that's what the fundamental counting principle just says, that we can multiply the number of ways each one can occur, and that's going to give us the total possibilities. So 4 times 2 times 2 equals 16 total possibilities. That's helpful. As I'll tell you, when you go to make this list on the side here with the possibilities, it's really easy to forget some. So it's nice to know the total. So let's do another example. So and this we're going to start talking about probability and percent chance here. Okay, so let's look at flipping a coin again. So we've got this coin, okay, it could be heads or tails, and we're asked what's the percent chance that it will land heads up? What's the probability? Okay, so when we do probability, and the formula is down below here. In fact, let me just scroll down right now so we can talk about it. So if we look down here where you see classical probability, in order to find the probability of something happening, so P of E, in this case, we're going to find the probability of getting ahead. Okay, that's just the number of outcomes, the number of heads. So this is just an example, divided by the total outcomes, the total number of outcomes or possibilities. Total outcomes, let's say possible. Okay, so that's what this says. We want the total outcomes on the bottom, okay, and then the number of times the event occurs on the top. So if we want the percentage that land heads, well, there are two options, heads or tail, and one of them is heads. So we say the probability of getting a heads is 1/2. We can also say 0.5. We can also say 50%. So 3 different types of numbers, they all represent the same thing. It's just a different way to write it. So a sample space is the set of all possible outcomes, and that's really important. So we wrote a sample space up here when we said heads or tails. So the sample space for a coin here is head, comma, tails. When you write the sample space, you use brackets and then you list out all the different possibilities. And that's helpful because when you go to do the probability question, it makes it so much easier when you have all the possibilities listed out. Okay, and then an event, or we could say outcome, is any subset of the sample space, and a subset is part of it. So this is just part of the sample space. So let's go ahead, and I'm just going to scroll down here and let's do a couple of examples. It's going to make so much more sense if we actually do some examples. So a single die is rolled, okay? Find the probability of getting the following. So the first thing we're going to do is we're going to write out the sample space. So the sample space for rolling a die, we use brackets, is 1, 2, 3, 4, 5, or 6. The order that you write those down does not matter. You just want to list out all the possibilities. So 6 possibilities total. So when you're finding the probability for rolling a die, you can just go ahead and write a fraction right off the bat and put 6 on the bottom because the total possibilities needs to go on the bottom. So the first one says, what's the probability of getting a 2? Well, there's 1, 2. Use a different color here. So the answer is 1/6. For the second one, a number less than 5. Less than means not including 5. So that means 4, 3, 2, or 1. So there are 4 out of 6. Okay, numbers less than 5. When you're dealing with fractions like this, you should always reduce. So we could divide these both by 2 and get 1/2. Okay. If you have a graphing calculator or a TI 30 and 34, you can use the fraction button, the N over D, and have it reduce it for you. You could certainly also put this as 0.5 into your into Connect, and it would accept that also. So the last one, an odd number, so let me just erase this here. An odd number would be like 1, a 3, or a 5, so that would be 3 outcomes out of 6, and we can reduce that to 1/2 or 0.5. Okay, you're not going to list the percentage unless Connect asks for a percent, and most of the time it's going to ask for either a fraction or a decimal. So just pay attention to what the directions ask you. So let's look at this example. So 2 coins are tossed. Okay, find the probability of getting the following. So let's, so if we have 2 coins here, I want you to visualize 2 coins. This first one could be tails or heads, and the second one could be tails or heads. So I'm just going to write out the sample space. So the sample space for rolling 2 coins, or I'm sorry, not rolling, flipping 2 coins, we could get a head and a head. We could get a tail and a tail. We could get a head and a tail, or a tail and a head. Those are all the ways to combine those 2 different options for the coins. So there are 4 total. options. So all of these fractions are going to be over 4. So the first one says, what's the probability of getting 2 heads? Well, that's 1 out of the 4. Okay, at least 1 head. Let's talk about what that means. At least 1 head means 1 head or 2 heads. Okay, anything 1 or more. So we've got 1 head, at least 1 head there. We've got at least 1 head there, and we have at least 1 head in that outcome. So there are 3 out of 4 that give you at least 1 head. And then the last one, at most 1 head, meaning we have 1 or less. So that option would work, that option would work, and tails would also work. So this one would also be 3 out of 4. All right, so let's kind of go through some of the probability facts. This can be kind of useful. One nice thing about probability is that the numbers that you get for probability, the answers that you get like on your homework, for example, when asked probability, are all going to be between 0 and 1. So if you get an answer for a probability question that's outside of that range, you know right off the bat that it's not right. So it's a good thing to just check your number, and if it's outside of that range, you know something's wrong and you should try it again. So 0 represents 0% and an impossible. So for instance, if I say to myself, you know, what's the probability that I'm in Hawaii right now? It'd be 0% because I'm not in Hawaii. As opposed to 1 is the same thing as 100%, and that's a certain outcome. So what's the probability that I'm making a math video right now? It's 100% because it's happening. And then you can be anywhere in between. So 0.5 is the same thing as 50%, or 1/2 as a fraction. And that would be, you know, sort of in between impossible and certain. So it could happen, it could not. Other probability facts. The sum of all the probabilities in a sample space will equal 1. So let's just kind of go up here and look at the sample space that we had here for the heads tails example. So if you think about what each of those probabilities are, so what's the probability of getting head? Well, that's 1/4. The probability of getting tail, that's 1 out of 4. Head tail is 1 out of 4. Tail head is 1 out of 4. And if you add those probabilities together, 1/4 plus 1/4 plus 1/4 plus 1/4, you end up getting 1. So, which is the same thing as 100%. So the probabilities of everything in the sample space individually added together should always equal 1. They're not always necessarily going to be the same number, but they will always add to 1. So that's what that's saying. And then the other thing, let me talk about the complement of an event. So E apostrophe, that's just the complement. I'm going to get a skinnier pen here. It's hard to see that. The complement of E. And let's talk about an example. So let's say S stands for it's going to snow. So let's say that the probability that it's going to snow today is 70%. P of S complement would be that it's not going to snow. So whenever you see an apostrophe, think to yourself, that means not. Well, if we know that there's a 70% chance that it's going to snow, then the probability that it's not going to snow is just 100% minus that, because total, the two probabilities together need to add to 100. So it's either going to snow or it's not. So the chance that it's going to snow is 70, and the chance that it's not going to snow is 30%. And that's what this formula up here is saying. Okay, so we can use decimals to write that out too. So the probability that it's not going to snow would be 0.30, and that's going to be 1 minus the probability it is going to snow, or 0.70. So I'm just going to leave that there. I think that's probably more helpful to talk about in the context of an actual problem. So we'll come back to that. All right, so let's talk about empirical probability. So we talked about theoretical probability, and let me just back up. I'm just going to show that one more time. So classical probability, that's the same thing as theoretical. That's the kind of probability where you just look at the number of options and you divide how many times something occurs by the number of options. So down here, when we're talking about classical or empirical probability, that's the kind of probability that you use, that you find from an actual experiment that happened. So you use the results of the experiment, not the possibilities of what could happen. So this is an example. So this is an experiment. Results here. So we took a sample of 50 people, and this table outlines all the different blood types, the frequency of each type of blood. And so we're going to use this table to answer the probability questions. Now, the really important thing here is to identify the fact that there are 50 people total. So in all of these probability questions, the denominator of the fraction is going to be 50 because there are 50 different total options for each one of these. So part A says, what's the probability that somebody has type O? Okay, so the total is on the bottom, 50, and let's find the number of type O to figure out to do the top. So if we look at the table, the number of type O is 21, so the answer here is going to be 21 out of 50. The next one, what's the probability that they're type A or type B? Now we haven't done one like this before, so let's talk about what or means. Or it means either or, so you count both. So you count the A's and the B's. So if there are 22 A's and there's 5 B's, we're going to actually add those together, and that's going to give us 27. So there are 27 over 50 is the probability that you could that somebody would have A or B blood based on this experiment. Okay. The C, we want the probability that a person has neither type A nor type O blood. The way we could write that is we could say A or O complement. Okay, we could do it like that. And so if somebody does not have A and they don't have O, that means they're either going to have B or they're going to have AB. And those together are 7 if we add those together. So the probability that somebody has neither A nor O is going to be 7 over 50. Okay, and last, the probability that a person does not have AB, so probability of not AB. So we could write it like this, AB complement, because remember that apostrophe or the complement just means not. Okay, so there are a couple different ways we could do this. We could look at all of the options where the blood is not AB. So that would be A, that would be B, that would be O, and we could add those up. So 22 plus 5 plus 21. Okay, and we can put that on the top and we get 48 out of 50. Now we can actually divide those both by 2 and we get 24 out of 25 as our probability. The other thing that we can do, if we didn't want to add up all those together, we could use the complement rule. So we could say the probability of not having AB blood is the same thing as 1 minus the probability of having AB. So if we look at the table, I'm going to erase this. If we look at the table, there's 2 out of 50 chance that somebody is going to have AB blood. So if we do 1 minus 2 over 50, which if we write 1 as 50 over 50, it would look like this. And then if we subtract these two fractions, we get 48 out of 50, which is the same thing we got up here. So we could either add all the ones that are not AB or do 1 minus AB, and either way we're going to get the same answer. So it gives us some options there. All right, so that was all of that first section here. We're going to scroll down and we're going to talk about 11.4, which is on tree diagrams, tables, and some sample spaces. So we're going to start by talking about a tree diagram, which is just a diagram that helps us basically draw a picture of all the different outcomes that you could get when you have a probability experiment. So let's think about what would happen if a family had 3 children. So the way you start a tree diagram, and you can do this vertically or horizontally, it doesn't matter, but I start with a dot and I ask myself, well, what could happen if we have our first child? Well, our first child, we could have a boy or we could have a girl. Okay, and then the family's going to have a second child. So if they have a boy first, they could still have a boy or a girl for their second child. Or if they have a girl first going down that first branch, they could have a boy or a girl for their second child. And then we're going to do it again. So we're going to start at the top. They could have a boy, they could have a boy, and then they could have a boy or a girl for their third child. So this third layer represents their third child. And these could also be boy or girl. So every one of these branches represents an outcome. So for example, if you start at the top and go down, you could have a boy, or a boy. So that represents boy, boy, boy. Okay. You could have a boy, boy, girl would be the second one. Okay. You could have a boy, girl, boy. You could have a boy, girl, girl. They could have a girl, boy, boy. They could have girl, boy, girl. They could have a girl, girl, boy. Or they could have a girl, girl, girl. So there are 8 different outcomes. You can also see that there are 8 outcomes by just counting the ends of all the branches, and there are 8 different end points here. So there are 8 different options. And the nice thing about the tree diagram is it helps us draw the sample space. It helps us it prevents us from, forgetting one. I could see just trying to make this list without the tree, it's easy to forget one of those outcomes. So now that we have the sample space written out, it's a little bit easier to actually answer probability questions. So let's look at this example. If a family has 3 children, find the probability that all 3 children are the same gender. So this is asking, what's the probability of having boys, 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 or a girl, and a girl? Okay, we know there are 8 different outcomes, and there are the boy, boy, boy occurred 1 time, and the girl, girl, girl occurred once. So there are 2 out of 8 times that occurred. We could reduce that to 1/4, which is 0.25. So either 1/4 or 0.25 are both good answers for that one. So now once we have the tree, you can see it's a little bit easier. If I asked you even more questions like what's the probability of having girl, boy, boy, you can look and see, oh, well, that's 1 out of 8 without having to make the list each time. Okay, so let's look at this next example. We're going to draw a tree for this also. So we toss a coin and then we roll a die. So the first part, coin toss, let's do that part of the tree. So we start at the top with our dot. We ask ourselves, well, if we toss a coin, what could happen? I could get a heads, I could get a tails. So this first layer here, this is the coin. And it doesn't matter which order we do this in. And then next, we're going to roll a die. So regardless of what happens on the coin, when we roll a die, we could get a 1, a 2, a 3, a 4, a 5, and a 6. And I'm going to do the same thing over here for tail. And then we can go down all of those paths and write down the sample space. So for the sample space, you're just going to go down. Let me get a different color here. You're going to go down each branch. So we could get a, whoops, not a 1. We could get a head and a 1. Okay. We could get a head and a 2. We could get a, whoops. We could get a head and a 3, a head and a 4, a head and a 5, a head and a 6. We could also go down the tail branch. So we could get a tail and a 1, a tail and a 2, a tail and a 3, a tail and a 4, a tail and a 5, and a tail and a 6. So it looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 total outcomes. So that helps us answer probability questions. So, So we are asked here, use a tree diagram to find the probability of getting a heads on the coin and an even number on the die. So let's circle any of the outcomes, and you can pause the video at this point and try to do it on your own. Circle any of the outcomes that have a heads and an even number. So it looks like that would be a heads and an even, heads and an even, heads and an even. So it look like there are 3 different outcomes out of 12 that would give us that probability, or give us that outcome. And that we can reduce by dividing both of these numbers by 3 and getting 1 over 4, which is the same thing as 0.25. And I just want to mention too, with the fractions in the calculator, you can do 1 divided by 4, so the division sign, and that'll give you your decimal as 0.25 there. Okay, so now we talked about tree diagrams. Let's look at using tables. So the standard deck of cards is a really popular table to use in probability. It just makes for really, I guess, not easy to do, but it's easy to create a lot of probability questions from it, so it's used quite a bit. So let's talk about this table and label this in case you're not familiar with cards. So we've got hearts. There are 4, we call them suits, diamonds, spades, and clubs. There's 13 of each of these rows for a total of 52 altogether. So there's 52 total cards. Okay, the first 2 rows, as you can see, are red. The second 2 are black. We've got some face cards. All of the jacks, queens, and kings are called face cards because these cards actually have faces of people on them. So let's do some examples. So for all of these, since this is a single stage experiment, and we call it a single stage because only 1 card is being drawn. In Module 8, we'll get a little bit more complex, but for this section, we're just going to draw 1 card, and so all of these probabilities are going to be out of 52 because we have 52 cards to choose from. So the first question asks, what's the probability of getting a jack? So you can simply just count the number of jacks in the deck. There are 4, so there are 4 out of 52 is going to be the probability, and then we could reduce that by dividing both by 4, and that leaves us with 1 out of 13. For part B, we want to know the probability of getting a 6 of clubs. Well, there's only 1 6 of clubs. It's right there. So there's a 1 out of 52 chance of that happening, and we can't reduce that. So we're just going to circle that. And then lastly, a 3 or a diamond. So this one's trickier because if you count the 3s, there are 4 3s. And if we count the diamonds, there are 13 diamonds, but we don't want to count that 3 of diamond twice. So I would just circle everything that applies and then count them and make sure you don't count anything twice. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 diamonds, 14, 15, 16. So there are 16 out of 52 that I circled. And then those 2 numbers are both divisible by 4. So that gives us a fraction of 4 out of 13. So I'm just going to write a note here. Let me just get this thinner. So don't double count the 3 of diamonds. Okay. All right, so we're going to look at one more chart, and then this concludes Module 7. So this is a handy chart that shows you the outcomes when you roll 2 dice. So the red and the blue just differentiate between the 2 die, basically, and then all of the different outcomes are in the middle. So for instance, like this outcome right here, that means you roll a 1 on the red die, and then you roll a 6 on the blue die. Okay, so imagine, 2 dice. The one has a 1 on it and the other one has a 6. So that's what that outcome represents. So if you look at this chart all together, there's 36 different outcomes. So there's 6 across and 6 down, so 36 total possibilities. Okay, so all of our probability questions down here are going to be out of 36. Since there's 36 different possibilities. So you roll 2 dice. What's the chance that you get a sum of 8? So let's talk about sum what sum means. So sum means adding, okay? So for instance, this first 1 and 1, this has a sum of 2 if you were to add those two together. So think about how you could get an 8. You can get an 8 by taking 6 plus 2 gives you an 8. 5 plus 3 gives you 8. 4 and 4, 3 and 5, 2 and 6. And it looks like there are 5 different options out of 36 that give us a sum of 8. So that's the probability. There's no common factors between 5 and 36. So that's the fraction. You can't reduce it any further. So let's look at doubles. So what's the chance of getting a double? So 1 out of 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So it looks like there's 1, 2, 3, 4, 5, 6 outcomes. And then that can be reduced. We can divide both of these numbers by 6. We get a 1 on the top and a 6 on the bottom. So there's a 1/6 chance of getting a double. And then lastly, a sum less than 5. So let's think about what the smallest sum would even be. If we roll a 1 and a 1, we're getting a sum of a 2. So what's the chance that you get a sum of a 2? You could get a sum of 3. You could get a sum of 4. Less than 5 means not including 5. Okay, so let's circle the options that give us a sum of 2. So 1 and 1 gives us 2. That's the only option. And then a sum of 3 is going to be 2 plus 1, 1 plus 2. 3 plus 1 gives us 4, 2 plus 2 gives us 4, 1 plus 3 gives us 4. Anything more, you can see it just makes kind of like a triangle here. Anything more or any higher numbers are going to give us a bigger sum. So 4 plus 1 gives us 5. That's too high. This is too high. All of the rest of the table, when we add those together, are greater or 5 or more. So there are 1, 2, 3, 4, 5, 6 different outcomes that give us a sum less than 5, and we know that that reduces to 1/6. So I hope that helps. Let me know if you have any questions.